You ever stop and wonder how the incredibly complex algorithms running on your phone, in your car, everywhere, how they actually become a physical piece of silicon? For decades, that process was slow, tedious, and completely manual. But today, we're going to talk about a technology that is completely changing the game in hardware design. It's called high-level synthesis, or HLS. Let's jump right in.
All right, so here's the plan. We'll start with the old way of doing things, what I like to call the RTL design wall. Then we'll get into what high-level synthesis actually is and why it's such a big deal. After that, a super important part, why your coding style is so critical. Then we'll look at how to squeeze out every last drop of performance. And we'll wrap up with the new mindset you really need to succeed with this stuff.
So to really get why HLS matters, you have to understand the problem it's trying to solve. For years, hardware engineers have been slamming into what you could call the RTL design wall.
This quote just nails it, doesn't it? The algorithms we're trying to build today, like a modern video decoder, are unbelievably complex. But the tools we were using to build them, languages like Verilog and VHDL, they were created for a much simpler time. Think old-school VGA controllers. The tools just weren't keeping up with the ambition. Something was definitely broken.
And this really gets to the heart of it. Writing RTL, or register transfer level code by hand, it's a slog. It's so slow. And it quickly becomes what one designer called a nightmarish iterative cycle of just hunting for bugs. You know the drill. You fix one thing, you accidentally break two more. Every single manual change is a chance to introduce an error. And as chips get more and more complex, this whole problem just snowballs into a massive development bottleneck.
Okay, so if the old way is broken, what's the fix? Well, this is where high-level synthesis comes into the picture. And it's not just a small change, it's a fundamental shift in how we approach hardware design.
So what is it? Put simply, HLS is a tool that automatically takes an algorithm you've written in a high-level language, usually C++, and translates it directly into that low-level RTL hardware description. You can think of it like the leap designers made ages ago from drawing circuit schematics by hand to writing RTL in the first place. This is the next big step up in abstraction. So, how does this whole thing work? It's not really magic. There's a process. It all starts with a C++ code from an engineer. The HLS tool reads that code and first creates something called a data flow graph to understand all the dependencies. Then, the clever part, it maps every operation, like a plus or a times, to an actual hardware block, like an adder or a multiplier. Finally, it figures out the timing for everything and spits out the final RTL code.
And this is what that starting point looks like. The beautiful thing is, the engineer doesn't have to think about clocks or registers or state machines here. They just write a totally standard C++ function that describes what they want to happen, like this simple little accumulator right here. And from that simple little function, the HLS tool automatically figures out the hardware structure. It sees the multiplication, it sees the addition, and it knows it needs to store that result somewhere, so it creates a register. It builds the whole circuit you see here. The engineer describes the what, and the tool figures out the how. Pretty cool, right?
Okay, so we know what HLS is. Now for the really good part. Let's talk about the payoff, the huge advantages this brings to any design team. I mean, the difference is just night and day. A design that could take you days, maybe even weeks to code by hand in RTL, an HLS tool can generate that in minutes. And instead of being locked into a single hardware architecture you've spent all that time on, you can explore tons of different options just by tweaking a few settings. And verification? Forget about slow, painful RTL simulations. You can verify your design with a super fast C++ test bench.
So when you add it all up, this is the real payoff. HLS frees up engineers to focus on what actually matters, the algorithm itself. It just slashes your design and verification time. It lets you play around with the design space to find the absolute best hardware for the job. And it means you get to spend your brainpower on innovation, not on manually wiring up gates and registers. But, and this is a really big but, HLS is not some magic wand you can just wave. To get good results, you can't just feed it any random C++ code you find online. How you write your code is everything.
Mike Fingeroff, who literally wrote the book on HLS, said it perfectly. He figured out early on that your coding style has a huge impact on the quality of the hardware you get out. You have to always remember, you're not just writing software anymore. You are describing physical hardware.
And this right here is what happens when you forget that. In software, you might think of an integer as having an almost infinite range. But in hardware, nope, it's a fixed number of bits.
And if you don't account for that in your C++, your numbers can overflow and wrap around, producing completely useless, garbage results like you see here.
And there are other classic mistakes too. Forgetting to initialize a variable can cause a mismatch between your C++ simulation and what the hardware actually does, or just casually throwing in a division operator without realizing that thing synthesizes into a giant, power-hungry circuit on your chip. And a big one, if your test bench doesn't test every single if-then-else path, you could be synthesizing a bug and not even know it's there.
All right, let's say you've got it. You're writing clean, hardware-aware C++. Now, how do you push it to the limit? How do you get peak performance? This is where HLS optimizations really shine.
One of the most powerful optimizations out there is called loop pipelining. The whole idea is to build a hardware pipeline that works like a factory assembly line. Instead of processing one loop iteration from start to finish, you have multiple iterations all in flight at the same time. The absolute goal, the holy grail, is to get an initiation interval, we call it II, of 1. That means your hardware is starting a new loop iteration every single clock cycle. That's maximum speed.
But you'll almost always hit a bottleneck somewhere. So in this example, say we're doing image filtering. For each pixel, our loop needs to read 9 neighboring pixels from memory. But the physical memory on our chip only has 2 ports. It can only do 2 reads at a time. So the HLS tool comes back and tells us, hey, because of this memory conflict, the fastest I can go is an I/O of 5. Not great.
So how do we fix it? Well, the solution is in the C++ code itself. Instead of having one giant array in memory for the whole image, we can be clever and partition it. We can split it into 3 smaller arrays. Just by making that change in the source code, we're telling the HLS tool to create 3 separate physical memories on the chip, each with its own ports. And check out the result. It's awesome. Now, each of those 3 new memories only has to handle 3 loads, and each one has 2 ports. The bottleneck is gone. And look at that. The initiation interval drops from a painful 5 all the way down to 2. We just got a massive performance boost in our final hardware from a simple change in the C++ code.
So, as we start to wrap this up, you can see it really all comes down to a new way of thinking for the hardware designer. It's a whole new mindset.
This right here is the key. HLS isn't about forgetting what hardware is, it's about using a more powerful language to describe that hardware. The absolute best HLS designers are constantly asking themselves this question. If I write this line of C++, what circuit is that going to create? They never lose sight of the connection between the code they're writing and the silicon that's going to come out the other end.
And that's really the final thought I want to leave you with. When you're working with HLS, are you just writing software, or are you architecting hardware but with a new, more powerful language? Once you make that mental shift, you're not just a programmer anymore. You're building the future of hardware, one C++ function at a time.